Hello, hello. Welcome to the next Bevy Meetup. I'm super excited for this one today. We're going to have three amazing speakers. I'm going to quickly go through our agenda, the typical intro. Welcome to the Bevy Game Development Meetup. Today we're going to have, this is the fourth installment, and today we're going to have three amazing speakers. Each are aiming to 15 to 20 minutes presentations. I think I heard already that we might have a little bit of overtime in some cases, but believe me, this is worth it. These are amazing topics. Each presentation will follow a little Q&A panel. Please use the QR code or the link in the comments or in the description to go to the Q&A platform. We will make time at the end of each talk, and then gonna go to a panel discussion at the end of the whole stream. Everything will be recorded and live streamed, but also gonna be chopped into individual videos later and released on YouTube. So, code of conduct, typical Rust stuff: be kind, be respectful, be curious, ask us everything that you're wondering about. And reach out to me if you have any concerns. You can find me on all these channels like YouTube and Twitter. My name is Stefan. I use Rust since 2017. I'm in the game development ecosystem on and off for 17 years already. You might know me for my open source work in Git UI and LifeAsk. That's the Q&A platform we are actually using. I recently founded Rust Unit, a Rust consulting shop. And if you want to know more, follow the link. Or reach out to me. Here is the QR code one last time. You will also find it in the corner here, I think, in the QR code. And without further ado, I would pull up our first speaker, François, on stage for today. Let me get that done. François, welcome.
Hello.
I'm super excited for your presentation today. Lots of insights into the infrastructure for securing the quality of the Bevy engine. So I'm happy and curious. So let me put up your slides here. Give it away.
Okay, thank you. So I'm starting today's meetup with how to catch all the rendering regressions on the Bevy engine on all platforms. So the question is how to test a game engine on macOS, Linux, Windows, iOS, Android, WebGPU, WebGL2, and all that in continuous integration. A quick word about who I am for those who don't know me. I'm MokersF on GitHub. I'm using and contributing to Bevy since the 0.2 version, so that was some time ago now. And I'm a maintainer and SME on several topics on the Bevy engine. If you have any idea how to improve the testing, don't hesitate and come talk to me. So how do we test a game engine? Of course, it's code, so we can have unit tests. Their goal is to test a specific function. In Bevy, the coverage is very low in unit tests. We are pushing more and more for adding them in PRs, so it's increasing. But at the same time, aiming for 100% coverage is not a good thing. It would just slow us down. Another kind of test we have in Rust is the doc test. They are the documentation test, and they are here to show how to use a function. But it's not made to test the engine, it's made to test the user experience of the engine, and they typically, for example, don't have any assertion. Another kind of test in Rust we have are the integration tests. They are here to test the public API and to test how different modules work together. And we have a few in Bevy. We can look at the test folder and notice that they are not actually tests for Bevy, but they are here to document how to test your game. So yeah, Bevy doesn't have an integration test at all. And the last kind of test we have in Rust are the bench tests. They can check the performance of a function, and it's easy to compare them between runs. Most of the bench tests we have are focused on the ECS. We also have a few on reflection and on async task, but yeah, it's mostly ECS. And the last part of Bevy for the test are the example. They are a big focus of Bevy because they are an easy way to demonstrate how to use the feature and to serve as a demo for the engine. We run a few examples in CI to catch crashes. So when an example crash, it will fail the CI job, and we will have to monitor. For example, we had a long time issue with reducing the window size to 0 pixel that was crashing everything. So we have an example in CI that will just change the window size to 0 and test that everything still works fine. And more, we are encouraging contributors to run the example related to PRs to check that they are working. Okay, but what about rendering? How do we test rendering in CI? Are we going to write unit test or integration test and maybe check that the rendering world has everything as expected, or that we are generating the correct command? Those kind of tests would be very hard to write, very hard to maintain, and very brittle. So maybe not the best idea. So I want to speak about visual test. The idea is to do snapshot testing. We take a screenshot before the change, we take a screenshot after, and we just compare them. For comparison, there are a lot of algorithms available. I mentioned a few here, but the main one I'm using for the moment is pixel by pixel because it's just the fastest and the simplest. I think I'm going to try using Flip from NVIDIA, mostly because it's quite cool how it works, but yeah, not yet. And the good thing is we can reuse the example. So the idea is to run every example in the Bevy repository, take a screenshot, and then compare the screenshot with the last execution on main. And the tool I'm using and yeah, of course, in Bevy, we have a feature for that. It's a feature Bevy CI testing that is introducing an easy setup that will make us have a constant frame rate and that is able to send event at given frame. For example, with this file, at the frame 200, we'll get a screenshot. At the frame 900, we will exit. The use for that was to make all the example determinist. So to be able to compare the screenshot, I need the example to render exactly the same at a given frame. So every example is using a fixed time step. And when you need something random to happen in the example, we are using seeded random so that it always happens the same. And the tool used for screenshot comparison is Pixel. It's an image comparison as a service. It was made with Bevy in mind by myself. And to be very fast and reduce cost, it first do an hash comparison of screenshots, and it will be pixel by pixel only when the hash are different. It's very basic for now and still evolving. Another thing that could be interesting are bench tests for the renderer. We do have some example for bench tests, the stress test, but yeah, for the moment, it's not possible to use them in CI. It's blocked on having actual hardware, but we could start by already writing the documentation and having everyone agree on how to run them to test the renderer. But okay, so we know how to test rendering, but really on all platforms, we have a few constraints. We need them to be in the cloud, headless, and reliable. So let's see with the GitHub runners. The first one is Linux. Okay, it's possible using LLVM pipe as a software renderer, XVFB to get a virtual X11 desktop. And this is the system info and the adapter info we get on this. So yeah, it's working. It's not the fastest. It doesn't have all the features and bell and whistle, but it's working. And we need to do something similar for Wayland. I started to look into it. It seems to be possible, but yeah, I don't have a lot of experience with Wayland. macOS, lucky for us, it just works on the new M1 GitHub runners. They were public maybe a few months ago, but yeah, they are very fast and they are working with a software renderer too. Windows, it used to just work, but yeah, it's degrading more and more. And it started with every example loading a GLTF file failing, and now just most 3D examples don't work. So I just disabled them since a few days ago because it was just giving way too much error. Windows is probably the less valuable platform in CI because we already have a lot of contributors using Windows, so we're trusting people to test them on their local machine. For Wasm and WebGL2, I tested many configurations in CI with different host OS and different browsers, and it works very, very well in CI with Ubuntu, with Firefox, again with the XVFB and LLVM pipe. For the moment, the scope in CI is very limited. It only runs 6 examples, and it's using a browser script with Playwright, that is a browser automation tool, and taking a screenshot, same, but this time it's not yet with a built-in feature to take a screenshot from Bevy, it's using the one from Playwright. Wasm and WebGL2, WebGPU, same thing. I tried all the configuration and I found that macOS and Chromium works in CI, so it mostly works like WebGL2. iOS, we are running tests on 3 versions of iPhones with 3 versions of iOS. And it's thanks to Browser Stack open source support, we are able to use the real physical devices. What we are doing is running the mobile example and driving the test with Appium, which is a mobile software testing tool. And again, we are not using the built-in screenshot from Bevy, we are using the feature from Appium, but I'm not sure it's possible to use the feature from Bevy this time because it will save the screenshot locally on the mobile device and then it will be hard to get it back. Android, same as iOS, thanks to Browser Stack, we can run on real devices. We are testing on 4 devices. But to note, the first one, the Xiaomi Redmi Note 11, it's broken at the moment because GPU preprocessing is not working on it. And yeah, with Android come a lot more limitations. Some GPU don't support MSA, some GPUs don't support shadows. It's a bit of a pain with the various GPUs and what they support. So how does it look? I will switch to my browser now to show you. So this is my repository when I run all the actions. I don't run them on the Bevy repository because it would take a long time and it would block pretty much every other action because as you can see, it's running a lot of jobs in parallel. This is all the job for native on Linux, then on macOS. This is all the various mobile devices. And this is the two run on a web GPU and WebGL2. So yeah, that's a lot of job running. And every run is taking 7 hours. When there was Windows, it was a lot longer. It was taking 14 hours to run everything. Once all the examples are sent, the screenshots are sent to my tool, Pixel Eagle, that allows us to compare screenshots. For example, if I take the latest run on Linux, I can see differences. Yeah, this example, it has a lot of differences, and I can compare screenshots between the last and the previous version. So yeah, a few shapes were added, so the example is different. As we can see, some examples have a lot of differences. It's because there are very, very tiny bits of difference. This is the auto exposure example, and yeah, it doesn't exactly render the same always. Same for the SSIO example. There are a few pixel difference on the edge and transmissions also. For this kind of examples, pixel by pixel comparison is not the best, and I will need to use maybe Flip. That should work better. And then the last tool is the example report. It's a static site deployed on GitHub pages that will list all the run and let me see the differences and where it crashes. So yeah, this is a new example. It didn't run before. This one did change. So we can see the different shape. As I was saying, on the Xiaomi, it's failing. And we can see everything like that. So auto exposure is almost every time changing on Linux, never on macOS. So that's one of the reasons I didn't investigate it a lot because I'm on macOS. By default, it's only showing the examples with some changes. If we click on that, we have all the examples, and that's a lot of them. And most of them are stable and working very well. So yeah, a few screenshots of the tools for people just looking at the slide. And what are the next steps? Not that everything is working like that. I want to be able to add more mobile devices, but I'm waiting for some bug that will soon hopefully be fixed. At least they are in the milestone for the next version. The linked here is a page of Browser Stack with all the devices they offer. The goal is to have a good coverage of various GPUs, OS version, and device manufacturer, mostly for Android. I also want to improve the WASM test because they are not yet in the report page. It's quite recent that I added them, and for the moment they only run 6 tests. I want to be able to run a lot of them. And yeah, I want to be able to take the screenshots through Bevy to not have the screenshot from the browser, but to be able to test rendering from Bevy. For error reporting, when an example crash in native, it's easy to get the log because I just have to read the GitHub job log. But on WASM or mobile, it's a lot harder. On WASM, it would be the browser console. On mobile, I would have to check the various logs of the mobile devices with ADB or the equivalent for Xcode. It's not easy. So I'm trying to hook up Sentry to get all the logs, all the error log in them. It's working fine, but on pause for the moment because as Windows was crashing a lot recently, I exploded the free quota on Sentry, so I'm blocked for the month to continue investigating on that. Another thing I want to add with the Bevy CI testing feature is to be able to send a command for keyboard or mouse input. For the moment, I have two commands. I have a screenshot and app exit. So I want to be able to simulate a keyboard or mouse to be able to change things or interact with the example. For example, in the anti-aliasing example, we can change the mode by pressing some keys during the run. So I would like to be able to press the key, then take a screenshot for each different mode. It would also allow me to be able to test different scenes on mobile because we have only one example. So the goal would be to have different pipelines and maybe a 3D scene, a 2D scene, something with different light to be able to test all that in mobile. More features that I want to add to the BVCI testing feature is a command to print diagnostic because when it's crashing in CI, it's not always easy to find why. So yeah, being able to print debug values would be very useful. And the next, and it would be pretty much allow us to do anything, it would be to have a command to run a one-shot system. We could have a one-shot system that would check anything on entities, on components, and crash if not valid. That way it would be picked up by CI. Or we could trigger complex change and change the scene, change the state, change everything in what's being rendered to test it. And that's nice, but yeah, it's only running every 6 hours and only if there is a commit in main. My goal would be to be able to run maybe a subset of all the example on each PR validation, and it would comment on the PR with the result. It would not block because, yes, sometimes change in the example are expected. There is a PR open for stat. It's not yet reviewed completely. It's not yet working as expected, but it's the first step. And as soon as it's merged, I will be able to continue. And finally, I want to improve Pixel Eagle. It's already nice. It's already working, but yeah, there are a few things I could improve. A better listing page of all the run, more comparison than just pixel by pixel, because for some example, it's not enough. I would like to be able to declare in your zone in a screenshot, for example, for mobile when there is a time displayed. I want to not get the difference of the time. And I would like also to have more users than just Bevy to help finance the servers that at the moment I'm paying by for myself, and to have more feedback and develop the tool into something more useful. So how can you help? For some of the next step, for example, the new commands with BVCI testing, we just need someone to do it. So yeah, come and open PRs. If we want to be able to run more tests, it would cost more money, obviously. So sponsor the Bevy Foundation. And yeah, if you think visual tests with Persigle would be useful for you, for your project or your company, come talk to me. Some closing thoughts. We are very near the end of what's possible for free. Running all the example is slow. When I wrote the slide, there were 241 examples. There are two more already since then. So yeah, it's always increasing. We have always more. It's going to be slower and slower. If we want to be able to run faster, we need bigger runner, more runners, and that's going to cost money. If we want to enable Windows again, we would need bigger runners. So yeah, again, more money. And some point in the future, it would be nice to be able to test against realistic configuration, not just software renderer. And again, it would cost money to have actual hardware. Some very basic calculation. So for the current workflow, it's taking all the minutes I just wrote, and it would cost $13 per run if I was using private runners. Luckily, I'm on the free tier yet, so I'm paying nothing. If you wanted to add that to the repo, to the Bevy main repo and run on every PRs, it would cost around $2,000 per month just for the CI. And it would be even worse if we had Windows back and use faster runner. I did a simulation, it would be around 4,000 or 5,000 dollars. And if we want to use hardware co-located in a data center, we need obviously to buy the hardware, but then co-location in the data center is around $150 per month. But the big cost would be to have an admin available, because we would need someone to be on call. So that would cost a lot of money. And again, it's just everything that I just presented is not just for the game engine. It's everything is set built-in in Bevy, and you can use it to test your game. Don't hesitate to test all your targets in CI. You test your shaders, test everything in the UI, test your transition, test your games. Thank you.
Wow, that's a lot of money that we would need. Thank you, François. Super insightful, and it's amazing to have this kind of test happening. Even I'm not even sure a lot of people were aware that this is running in the background. Since when is that the case?
I started with simpler version a long time ago, maybe 1 year ago, but yeah, I'm always adding things to it.
Oh, wow. Okay. So we have a few questions in the Q&A platform. I'm going to just pick the first two, and then we save the rest for later so that we can give the other guys the stage. The first question, pretty straightforward. Can't the foundation get funding by AWS or similar cloud providers, I guess, to run all of that stuff in their device farm?
We could, but I think to get from a big corporation like that, we need the official non-profit organization, which we are still waiting for.
Oh, I thought this is all done now. Okay.
No, we did the paperwork, but we're waiting for the IRS feedback.
Gotcha. Okay. Well, that would be a promising way to handle this problem, right?
But yeah, we're already lucky because we're funded by BrowserStack to test on real mobile devices.
Yeah, that's already amazing to have. And the second most voted question is, do you have an example of a bug that we caught using this system?
For rendering bugs, yeah, there was a few. Well, to be fair, check most of my peers, because most of the time now they're just to fix bugs. Very recently there was not a bug, but yeah, we did a change in exposure on emissive materials. So the lava, for example, was looking a lot brighter. So yeah, that's something that I fixed. But yeah, for time to time we are losing the UI, or we are losing some part of rendering, or some shaders don't work anymore.
And as a side question following up on that, how much work is this in terms of maintenance that goes to there's actually something that got broken versus this is a false alarm, or this is an intended change that is following a PR that someone did?
Not that I removed Windows, not a lot.
Quite some Windows bashing here. Okay. Cool. Yeah, I would say we save the rest for a panel conversation at the end. Thank you, François, so much. I think everyone in the community is super grateful for your work in there, and especially it shows in the quality of the releases that we see that this is getting more stable and stable with every release. So, François, thank you so much for your presentation.
Thank you, and enjoy the rest of the meetup.
Okay, let's get ready for the second talk. We will have Lorenz on stage pretty soon. He is a fellow German, very much working with Bevy and known for a couple of traits that he's maintaining. And one of my personal favorites, a 2D particle system accelerated by GPU instancing. And I think we might hear a bit of that today in his presentation, because in order to do this, he had to dive into the rendering pipeline of Bevy. So I'm super excited. I never had a chance to do this myself very much yet. So I'm definitely going to learn something today. Lorenz, welcome.
Thank you for having me. Yeah,
here are your slides.
We started with rendering, and we are going to continue with rendering, but now we are going to look into the pipeline of Bevy. some sentences about me. I'm Lorenz, aka Lomix. I'm just a hobby game dev. I'm not a maintainer. And as Stefan said, I made a particle system. And I'm really interested in the rendering works of Bevy. So before we start with looking into Bevy, we have to do some groundwork. We have to look how the GPU actually sees the world and what it does expect from us, the developer, to display stuff on the screen. So the very first thing, vertex or vertices. These are just points in 3D space. We pass those points in 3D space to our GPU, and then we say how they are connected to triangles, for example. Finally, these triangles are then projected into 2D space, and then for each pixel that is visible in 2D space, the fragment stage is called, and we have an image. Okay, we start with our vertices, indices, and instances. Those are the first steps in our rendering. We pass these points to our GPU. These are called the vertices. As mentioned earlier, these are just points, 3D positions in 3D space, followed by the indices. Since, okay, I have to, yeah. How do I start? How do I say it? Okay. When we render something like a cube visible on screen right now, these points, these vertices, are used multiple times. So for example, the middle one is connected to 3 other ones. Since we want to tell our GPU these connections, but we do not want to pass these points in 3D space multiple times. That's where the indices comes in. So first we pass in the list of the points, and then we pass in a big array of indices that describe the order in which these vertices are connected. And finally, we have the instances. This just describes how often the same vertex is drawn. This just probably makes no sense right now, but we will look into it later. And finally, the next step is the UV mapping. How do we get a picture on those triangles? For this, for each vertex, we pass a 2D value between 0 and 1 on X and Y. And these describe a position on a 2D plane. And this 2D plane is usually a texture. That's how we get the data on it. And this whole process, we do not have to do ourselves. We just define the points of each vertex. And then the GPU will calculate it for each pixel, and we can exit it in the final fragment stage where we draw the texture. These steps in between are called the rasterization process from the GPU, when we go from the vertex stage to the fragment stage, and we don't have to care about that. Usually the GPU does it for us. And the whole process of this is called a pipeline, so describing which data goes in, how this data is laid out in memory, and how the GPU should interpret this is called a pipeline, so the whole configuration part. Also, yeah, on the screen right now, you can see the different stages. We first start with the vertex input, which usually consists of our instance data, our vertex data, and our index data, and everything else we want to bind per index or per instance, followed by the interpretation in form of the shader code, and then our superglobals that are accessible to each stage if we define so. These are called the uniform buffers. Usually there goes our textures. And finally, the whole configuration part, how the GPU should interpret these data. So how does it look like in Bevy? First things first, there are actually 2 worlds in Bevy. When you create a game in Bevy, you usually have your systems running in the so-called app world. And in parallel to the app world, there's another world you do not have access to right from the get-go unless you specify so, and that's called the render world. The render world will typically sync in a special schedule, the extract schedule, together with the app world. And there, all the data from the app world that we want to render will be copied over to the render world. And there it will be further processed to finally being rendered. The most important resource in this render world is the so-called render graph. This is describing the whole order in which the Bevy will render each different aspect of our world. For example, the 2D part, the UI part, the 3D part, the post-processing parts, and everything else that goes into, like Bloom. Each of these things are a node on the render graph, and the render graph's main purpose is to bring order to these things, so everything is displayed the way you want it to be. For example, you usually want to have your eye at the very, very last stage, because it should be an overlay over your actually render world. These nodes on the tree just implement the node trait, and the most important function on this trait is the run function. And there, every node is given access to the render graph context, which holds the previous and next inputs and outputs together with the render context. This is the connection to the GPU, and of course, an access, read-only access to the render world. This is where we copied our data to. So, inserting a pipeline. Now, we want to create a custom pipeline, of course. How do we insert it into this whole structure? Usually, we don't want to create our own node unless we want to do something very specific. Usually, we want to extend an existing render phase to make something draw on the screen that works well with the rest of the screen. For example, when you have a sprite and you have something custom you want to draw, and the sprite pipeline doesn't give you access to that. For example, you want to have a spline. Spline renderer is not part of Bevy. You want to implement that, but you want to make sure that your splines are still in order. So when a sprite with a higher C index is drawn on top, it should be under this sprite. So we have to make sure that our pipeline is running in the correct order. And by this, we are adding it to the right path. In our example, we will look at the transparent 2D render phase. And that is basically the one that is, I'm missing the right word for that. It's the one render path that deals with all the sprites and material 2Ds. And the way it works, the main path, the node on the main path 2D, which will render all these sprites before bloom is happening or tone mapping, will query each camera or view that is currently active. And for each camera, each view, there will be another component on the render world, the render phase component. And this render phase component will hold a bunch of items, the so-called phase items. And each of these phase items describe an entity, they hold a reference to an entity, literally, that will be drawn on the screen. And together with this entity the phase item holds, there is also a link or a reference to the used pipeline to render this item and the draw command that is necessary, as well as the sorting. So the phase item's main purpose is not only to know how it's drawn or how it's rendered and which pipeline to use, but also in which order. The whole render process happening in the render world works step by step. The first process we already covered is the extract step, where we copy the data from the render world, from the app world over to the render world. After we did that, we did determine for which camera these items are being rendered by calling the queue stage. In the queue stage, we get all our cameras or views and add the items that we extracted to the appropriated view render phase. After we have decided what to draw and add it to the appropriated camera, we start preparing the data, meaning we have our transforms, for example, and we have to make sure that these data objects are getting cast into a data format our GPU can use. That's called a buffer, and they usually have to be compatible with a C-style struct, and that's exactly what is happening in prepare. We are taking our data, do maybe some computation first, and then we're going to write it to the GPU buffer. And in the final stage, the draw call, we then tell our GPU, hey, we have a buffer, it's there in your memory, take it, bind it, load the shaders, and start the actual draw call. Oh, I just talked, yeah. We just talked about the extract stage, right? And the queue stage, here's another image showing it exactly. We have multiple cameras usually, or maybe you have multiple cameras, And for each of these cameras, we have to decide, we have to add a face item that means an item that is to be drawn for this specific camera. And these face items hold a reference to the entity in the render world, as well as the pipeline, the sorting, and the actual draw command. And the preparation, here we see it again. We take the data that we already extracted from the app world, and we prepare it for the WGPU buffers by doing whatever we need to do to our data to make it work with the memories. Yeah. And then finally, we have a draw call, which is in Bevy's context a tuple derived of multiple draw steps. We set the active pipeline. We then bind our first piece of data to our shaders by, for example, in this example, the view bind group is the all the transforms and projection matrices of our cameras, for example. We bind that as a uniform buffer so we can access it in the shader, and then we bind the texture we want to use, and finally we fire the draw call. Now, let's look at an example and see it in action. This was a lot of work and not a lot of work, a lot of words and many information that is probably very confusing. So the best thing we can do is to look at an example to make it a little bit more clear. For this example, we choose a very, very simple sprite rendering. So we basically implement our own sprite rendering using the Bevy icon, and we apply a simple vertex animation to the final output, which just squashes the item. We start with creating the components that live in our app world that we then are going to extract into our render world. And this is just a simple component in this case that holds a reference to the image we want to render. And we are going to use Bevy implements or provides us with some very handy macros. The asBindGroup macro in this case that makes it very easy to convert this type of data structure in a WGPU buffer that our GPU can use. So it makes our lives a lot easier as developers by taking away all the boilerplate. We can call a simple function on the struct, and it will just spit out a buffer that we can then use to send over to the GPU. There's also another macro, the shader type. For those who ever used the material traits before, they probably know this trait. Together with the asBindGroup trait macro, you can use it to create, as said earlier, data structures that you can easily bind to the GPU and send over without much hassle. So the second component is our pipeline. This one does not live in the app world. This lives in the render world. We are going to add it to the render world, and it holds the bind group layouts. These are the information about the memory layout of each of our data structures we want to bind. In this case, the view layout holds the information about our current camera, our perspective into the render world, and the second one is the uniform layout. In this case, it holds our image. And the third is the reference to the shader we are going to use and run. And also together with our pipeline, we define our pipeline key. This is just something that we can use to access our pipeline, our cache pipeline later on in the shader process. And also you can bind some data to it. Usually it's used for some sampling configurations. But for now, we just keep it empty here. We just want to have it as a simple way to get our pipeline from the cache pipelines later on. So the mesh. Instead of using Bevy's built-in mesh, we're going to use our own because it's a very nice example and shows us how the buffers are working, how the vertex buffers are bound. So we are going to create a fixed squad mesh here that is a resource. This resource will be just loaded once because for our sprites, we always pretty much want to just render a quad and then bind the texture on that. It's not going to change. So we're going to create a resource, and we're going to use two vectors to store our data. The vertex buffer holds the points that represents this quad. In this case, it's a point for each corner, and the index buffer holds the order in which the lines are connected between those. So we're going to implement the from world trait for this one. because, as I said earlier, it will just be loaded to the GPU once. We don't have to modify it in any way, shape, or form. The values will be kept between 0 and 1, and we will stretch it later. So we are going to get the render device and the render queue. The render device resources in the Bevy render world is just the configuration of your current GPU hardware. And the queue will let us queue up commands that we are going to send. In this case, we are going to create the two buffer vectors, which are just regular vectors, but with the addition that we can bind them or send them over to the GPU. Makes it very easy again for us. And we are just going to make our quad mesh in form of 4 points and directly write it to the GPU. So the memory is now on the GPU, and we do the same with the indices. In this form, we have a list of 6 indices, because each triangle is composed of 3 connections between 3 vertices and 3 lines. And the indices describe the index into the vertex buffer, so to say. So each vertex is just an array, and the index just is the list of, as the name implies, indices into that buffer to get the order right. So configuring the pipeline. Now that we have our data, we want to tell Bevy, or rather RepGPU, WGPU, how our pipeline is looking, how the connection is working, and how the interpretation of the data we are going to send is working. We already have our pipeline defined. We also implement the from world trait for our pipeline. We are going to get the render device again, because we need the configuration of the actual hardware below. And then we are creating new bind groups for that, meaning we are telling WGPU, or our pipeline, better to say, how the data that we are going to send is going to look in memory. And the first one is the view layout, which consists of the view uniform and the globals uniform. These just hold the data from our camera. These are directly from the Bevy core. I didn't make these my own. So there's the projection matrix and all the position of the camera and all the information that we are going to need to get the right angle on our 3D world later in the vertex shader. And also we are going to create the uniform layout. And now, since we implemented the as bind group macro on our structure, we can easily just call the bind group layout, pass our render device, and we just get the layout back from that. Makes it very easy. And of course, I haven't highlighted it, but we are going to load the shader from our asset server, which we got earlier, and pass it onto our pipeline resource that we then gonna add to our world. So next, we are going to implement the specialized render pipeline trait for our pipeline. This one will describe how this pipeline is going to work. And since the pipeline is, when this is called, the pipeline is already created. So the data we just prepared is already accessible to us. We have a reference to self, and we're going to use that to create a new render pipeline describer. This one is directly from WGPU, just wrapped in some Bevy-specific stuff. This one will describe the whole working of the pipeline. And to that, the first thing we are going to do is we are binding our uniform buffer, consisting of the view layout of our camera or view, and of course, of our texture. Then we are going to find the vertex state. This will be the first entry point into our rendering. We are going to find the shader that this vertex state is going to use. We keep it very simple. We just define the function that it's going to call it. It's called the vertex, so we just leave it at that, and we are not passing any definitions or extras in there. The shader definitions can be used to bind specific information, like, for example, MI, WASM, or WebGPU, WebGL2, and then we can specify values for these specifics and then access in the shader to make some if conditions. For example, WebGL2 has a very specific requirements on the layout that they are probably aligned in a certain way. So we usually have to do some padding there for our values, and we can pass these. We can pass some Boolean values there and say, hey, you are WebGL2. Please add some padding here and there for the buffers, so they are probably aligned in memory. But we're not going to do that for this example. We just leave it empty. So now we are going to define the actually input data for our vertex state. And the very first one we are going to bind in the first slot is the information about the position of each of these vertex or vertices. And it's just a simple vec3. So we are going to say that the value just holds a single float 32 times 3, meaning a simple vec3. And we are going to tell our GPU how much byte that is in memory. And we say the most important part, we are setting the step mode to vertex, meaning that this value is bound to each vertex. The next vertex will probably have a different value for that, and that's kind of important. And together with this vertex buffer, we are going to bind our second vertex buffer, and this one is not specific to the vertex, but to the instance. And meaning that each vertex of one model will share this information, and this information consists of the actual transform of our sprite in form of the translation, rotation, and scale. Also in vec4 format, we will construct a transformation matrix from that on the GPU and multiply it to set it in the right location later on. After the vertex state is defined, we are defining the fragment state. The fragment state will just we will just pass. It's mostly happening on the GPU. We already know what we are going to get, because what we are going to get we will going to define on our vertex shader. And all we have to say here is we link the shader we are going to use, and we specify the target. In this case, the target is an image of a specific format. That's the Bevy default texture format. Usually, you would also add, since we are extending the mesh-to-D pipeline here, you would probably create a copy of the mesh-to-D pipeline in the from world constructor of your pipeline and load this kind of information directly on the pipeline you're extending. And if you don't, you have to do it yourself. And if you fail at that, the program will crash. Same goes, the next step is the primitive state. Here we will define how the GPU will interpret the data going in. And the most important part here is the topology, where we tell the GPU that the array of indices we are sending represent a triangle, meaning three consecutive, three indices in the row construct a triangle. There's also different kind of ways to interpret. We can basically make a line, for example, but the triangle is the most common one. And also the font phrase, we are just going to ignore that for here for our example, because we don't need it. But the font phrase define in which order the indices go. So if they go counterclockwise, we are looking at the front side, and if they go counterclockwise, we are looking at the back side of a mesh. This is important for the cal mode, so we can remove stuff we don't see anyway, but it's not important for the example. So we're gonna leave it at the default. And the very last part is the multi-sampling. Here we define how many samples we are going to take from the image. And also, this is usually something you would load from a preloaded pipeline. In this case, as mentioned, the mesh-to-D pipeline, because it's set to 4. And since the path is running all on the same, it is required that these have the same values. So make a mistake here and the whole program fails. But we didn't do that because I wanted to show how it's done in general. After our pipeline is then described, we go over to run it. So back to the different schedules of the render world. The first thing we are going to do is we're going to extract our data from the app world. And for that, we are just going to create a simple system. And the data that we want to use in the render world, in this case, the extracted sprite instance, which holds our transformation matrix and the C ordering. So we know if it's, and the C ordering. In this case, the C ordering just consists of the C position of our transform. And we are going to create a new special variable, the sprite transform matrix, that will hold our transformation matrix in pod style, as we are using the byte mu crate here to make this struct compatible with C style structs. Pod just stands for plain old data, so it's a very simple type of data that the GPU can handle, and it makes it very easy for us to bind it later to the GPU buffer. So we are going to query the app world, and since we are currently running in the render world, we have to wrap our query in the extract struct. So the Bevy knows that we are actually accessing the app world. We are going to get the global transform and our custom sprite together with the view visibility. And then we are just going to iterate over all our entities, check, are they visible? If not, we just continue. And else if they are, we create the components we just created for our render world and just copy the entity over and insert these components into it, and the rest is empty. So the queue. The next step is the queue. Here we want to get all our views or all our cameras, and we want to add for each camera that has that can see our entity, we want it to the render phase of this entity. So we're just going to get get all our pipeline information. We're going to get the render phase from all our views together with the visibility of the visible all entities of these views and our extracted data. We're then going to get our draw function from our cache, and then we're going to iterate over each camera view. And for each camera view, we create a new specialized pipeline. And then we are going to go over each of our entities we just extracted, check is this entity visible in the current camera. And if so, we are going to add the so-called face item to the camera face, meaning, hey, you are going to get rendered by this camera. And we pass the entity, the pipeline, the draw function we want to use, the batch range. We are not using the batch range, but it's just something of the transparent to the pipeline phase that determines how often this thing is drawn. After it's queued, it's time to prepare our data. So the queue phase, after the queue phase, we are going to access our data again and prepare it for the GPU, meaning we are going again with our data, extracting it from the render world, and together with all the information that our GPU needs to bind data. We then iterate over all our extracted sprites and transform the appropriated buffers we want to have. The first one is the instance buffer that holds our transform data. We're just going to create a draw from a buffer describer. It's also a web WGPU thing that will hold our data. And then we are going to create the uniform buffer. Again, since we implemented the as-bind group layout, the as-bind group macro here, we can simply call a function that is very ready to use for us. We are just passing our layout information, our render device, the image, the render assets, meaning the GPU images and the fallback. And then finally, we're going to insert a new struct into our render world, into the entity, and that is the prepared version of our extracted data in form of the uniform buffer and the instance buffer. So finally, we enter the final stage of the draw. Since the main path of the render graph from the node to the render path will proceed to call the render command for each face item, we define the draw command as a tuple consisting of each of the steps necessary to bind the data and draw it to the screen. So on the first step, we are just readying the pipeline by saying you are active now. Then we are calling a built-in function from Bevy, a part of the mesh2d pipeline. We are this is just a simple function that will bind the already extracted few parameters of our camera to our data, to our pipeline. And of course, this is also happening inside of Bevy. We don't have to do it ourselves. And then we bind our uniform data in form of our texture, and finally our draw call. Let's go into the steps and look exactly what is happening here. The first one is the bind group. Here we implement the render command for a struct we defined, the set bind group struct, and this just has a generic implementing a constant, and this constant stands for the grouping we are going to use. In this case, it's group 0, standing for our texture. And we are going to implement the render command. The render command is implemented on a face item, and or 4 face items, better to say, and is called then by our main 2D path. And it will, we define the parameters. Since each face item holds an entity, we can define what data we want from that entity. For the entity, there's the item query, and we want to have access to the prepared data we prepared earlier, in this form, the prepared sprites. And we don't want any resources or information from the view. We just want to prepare data, and we're going to unwrap it, safe unwrap it, look if it's there on the entity, and if so, we are binding it to our render path, which means we are sending the first command. We say, hey, you have some data in your buffer. This one is relevant, bind it to the next phase of our rendering. And then we do the final draw call. Here we get, this time, our mesh we already prepared in the very beginning in form of our resource, and also the prepared sprite again. We're just gonna unwrap this data since it's a Rust thing, and there are a lot of lifetimes in the way, we unwrap it into the inner part of that resource where we have access to the index buffer and the vertex buffer we defined at the very beginning. And we then just gonna tell the GPU, since it's already there, hey, you have some data there, please bind it to the appropriate slots for the next phase. And when all that has happened, we finally tell our GPU, okay, the data is bind, you have access to everything, it's finally time, draw something. And here, the first parameter, we just gonna pass 0 to 6, which means draw the first 6 vertices, followed by how often we are going to try the instances. And in this case, since we just have in this example just one instance, the sprite instant count is just 1, meaning draw the first 6 vertices once, basically. Now we are going to put this all together in our final plugin, where we define all these stages. So this is how it looks, where we are creating a new plugin. And the first thing we are going to do in our build step is we are going to need writable access to the render app, which is a sub app of our normal world. And to this render app, we register our new commands. First one is our draw command, and we want that on the transparent 2D face item. The face item, the transparent 2D is the implementation of a face item specified for the transparent, for the 2D space, for everything that is 2D and transparent, I guess. And we are going to initialize also the pipeline in form of our specialized render pipeline. Then we are going to add our extract system that we already covered, and then the different systems running in the render schedule. The first one is the queue, then the prepare one, and that's about it. The rendering is done on the render graph that we don't have to deal with here. And finally, our data in the finish function of our plugin, meaning when everything is loaded, since we usually want to have access to, for example, the mesh 2D pipeline in this case, and access some of this configuration, we initialize our pipeline and our fixed mesh in the finish function. That's about it on the Bevy part. Finally, we are going to look on the GPU part, how to interpret this data. And for that, we have already created a shader. And the first one is, the first step is defining the input variables that we already bound. And in this case, in the first group is our view together with the globals. These come from the Bevy function, the Bevy render command function to bind a camera view that we used. And the second group is our texture. Then we define our vertex input. This is the data that we sent over into the vertex state. And this just consists of our 2 buffers. The first one, the vertex buffer, holding the information about the point in 3D space. And then the instance buffer that is the same for all vertices of this model. And this is the transformation, rotation, and scale, the translation, rotation, and scale. And then we finally define the output. The output of our vertex state usually goes, well, it always goes into the fragment stage with then finally will cover each pixel, pixel by pixel. And for that, all we want to have is the clip position that we have to pass, so the rasterization stage knows which pixels are visible and which are not, and the UV coordinate, which represents a point for each vertex on a 2D plane, which then samples the final texture. Whew, that's a lot of words. Okay, the vertex stage. Here we take our vertex input, and the first thing we are going to do is we take the instance input for each vertex and compute a transform matrix. And that's this part here. We don't need to know how it's going to work. It's not important. Just know multiplying matrices usually results in a position in 3D space. That's all you have to know. And we are also reading the texture size because we didn't pass any information about the size of our quads. We just render a texture, and we want to have this texture the same size as, we want to have our final render product to be the same size as the texture we are passing in. So we're reading the texture size here. And then finally, we also going to create some sort of animation item. In this case, we are just going to take the sine wave of the time that is also passed with the view buffer and make it positive, give it a minimum of 0.2. So our final quad looks like it's getting squashed. Then we define an offset. Since our mesh data is between 0 and 1, technically the center would be in the down left corner. And we want to make the center of the quad the center of the screen. So we're going to offset the position by half on each axis. Then finally, we compute the actual position from the perspective of the camera by taking our view projection, multiplying it by the instance transformation and the position of our vertex together with some multiplication of our animation scale on each size. So yeah, that is covered. And then finally, we are going to take, I forgot to highlight that, but finally we are going to create the view, the UV, and this is just the position of our vertex. In this case, since we defined them between 0 and 1, we are just going to pass the UV as the vertex data. All we have to do is inverse the y-axis, so our picture is not upside down. And this is all we are going to return. And then we are going to pass this to the fragment stage, and the fragment stage will just sample the texture given the UV coordinates we just passed. And this finally will result in an image. And this is basically all we have to do on the Bevy part. When we create an object, we are just spawning the spatial bundle, which just consists of the transform and visibility components, and then add our custom components with this byte to that. And that leaves us finally with a rendering of a sprite, of our own sprite pipeline, not using something from Bevy. And we are binding a texture and displaying a little vertex scaling animation on the y-axis. Ooh. Sorry, was a little bit rough, but that's about it. Yeah.
Lorenz, wow, what a intensive run through tons of code. I had no idea that it takes so much work to come up with a custom render pipeline.
It's strange. Yeah, it takes a lot of work just to display a texture. Yeah, that's just displays the power of a rendering system in general. How much it abstracts away from the complexity of the whole thing.
Yeah. Lorenz, thank you so much for presenting this. I heard that a couple of people will use that as a reference because they are having a project to create a custom render pipeline at some point. So yeah, I'm happy to see that you've put this example also on GitHub so people can follow along and play around with the code and a working example.
Exactly. Yeah, I imagine that this is a little bit too much for a talk. So at least I want to leave some sort of example that if you're interested in creating your own pipeline, you have something to start and maybe some information to have a rough understanding of the systems in place and why they are there.
Yeah, let's say I've seen a ton of questions. I would pick out the top one now, and we save the rest for the Q&A at the end. So how did you figure all of this Bevy specifics out? Did you read the code, or is there a good onboarding guide for the rendering?
There is, well, basically, Bevy is pretty much a very fast-moving engine. Every few months, we have many changes, especially in the rendering department. So most of the guides out there are usually, or information you find are usually either outdated or only cover half of the truth. So the reality is you have to really get into the engine part and just open the Bevy repository and look how they do stuff. There are tons of really cool tricks used there, especially in the sprite pipeline that is not common sense and not easy to understand unless you really dig into it.
But you would say it doesn't take a PhD to understand that code. It's
Definitely not.
Well documented and
just some genuine curiosity.
Yeah,
that's all.
Well, that's encouraging, because I guess your talk will also be outdated otherwise in a few months.
It will probably be, yeah.
Yeah. Lorenz, thank you again. A big hand from everyone in the stream for this presentation, and a great onboarding guide for the rendering pipeline in Bevy. I'm gonna put you down stage now, and we're gonna continue with the next presentation. We have to get going here. We are running out of time.
Oh yeah, sorry.
Okay, it's time for our last talk. Jos will talk about his project, very ambitious project, which everyone, even unconsciously probably, will be aware of based on the Bevy release notes from version 0.12, I believe, where we all saw his beautiful picture on top of the release notes. So let me put Jos on stage and let him talk about his Bevy project. Jos, welcome.
Hi, glad to be here. Thanks, Stefan, for that lovely intro. My head's still spinning from the last presentation. I'll have to
luckily you won't talk about rendering, right?
Yeah, luckily only mesh transformations and procedural modeling. So
okay, yeah. Take it away.
Thanks, thank you. All right, hi guys. Thanks for having me, and thanks for sticking around. Today I would like to present to you guys my journey in recreating Townscaper using Rust and Bevy. So I wish to share with you guys what the inner workings and what the thought process looks like of a medium-sized Bevy project. And hopefully this inspires someone here to try some procedural modeling of their own. So let's dive into it. So on today's menu, I'd like to first dive into what's this Townscaper all about, and why is this guy so obsessed about it. After which I'll dive into some specific challenges in this project. Sadly, we won't have time to really dive deep into some of these challenges, so do ask questions, and maybe we can dive into those a little bit later. And at the end I'll show a little online demo, and stick around because there will be a link for everyone to play around with what's out there currently. So what's Townscaper? So once upon a time, a little younger version of myself came across this amazing little tool called Townscaper. And I think the best way to explain what this tool is just to show a small video of it. So Townscaper is a organic creative building modeling tool created by Oscar Stallberg. And it's really just a procedural modeling tour de force. It took the world by storm. And the interesting aspect of this tool is it made some really complicated ideas and algorithms actually very playful and accessible to a very large audience. This tool is very easy to use, and almost anything you make in it starts to look beautiful. And yeah, as I mentioned, it's made by Oscar Stolberg. And the great thing about Stolberg is that he shares a lot of methods that he used to make this. So the blueprints are pretty much out there to, recreate this. So I saw this, and I just thought that the world needs more of this. You could make city planning tools out of this. Townscaper doesn't really have gameplay, but what if you would add gameplay to all of this? And being Dutch myself, I was reminded of how the structure of those cityscapes resembled a Dutch inner city. So I was really curious to also apply Townscaper to a Dutch context. I'm still not sure which one of these three things I'm making, but let's make it. So the plan is to shamelessly create a Townscaper clone and then extrapolate from there. With the whole idea of first imitating and then from there emulating and innovating, starting something new from there. What were some challenges along the way? Well, the first one is the task is huge. This is a huge project and not something you can easily just start with. So there are many components to the procedural system that makes up the Townscaper tool. Which is a irregular partition, so an irregular terrain. Then a lot of tiling systems that play with that irregular terrain and make up the entire world that you see. Some really interesting asset pipelines in there as well to make sure that you can actually create those models to be reconfigurable. Then there's a very interesting algorithm in there that I won't dive into specifically today because it will take a whole another talk to really digest, called the wave function collapse algorithm, and many more. So how do we solve this? Well, divide and conquer. So the only way to tackle a problem this big is to make, to my mind at least, is to make small tiny demos and then slowly build a repertoire of procedural modeling tools from those small demos, and then afterwards try to compose them into the whole that is this whole environment. I started out with TypeScript and JavaScript and did some quick hacking around just to get a sense of some of these subcomponents. The project is still out there. You can visit this link. I'll share this link in the chat shortly if you're interested. But you'll see some really rudimentary versions of the stuff that you are about to see. These are some of the demos. So this is a marching cubes algorithm, just a way to make some terrain. This is actually wave function collapse for those who are in the know-how, and just some rendering tools and a sort of prototype that's starting to look like the spherical project that you saw in the beginning. But that TypeScript and JavaScript environment had a bit of a, it had a ceiling. So I decided to transition to Rust to just gain a lot more performance, a lot more precision, especially for some of these procedural modeling algorithms. You really want to dive into specifics. JavaScript was just not cutting it for me on some of those algorithms. And why not C++? Well, Rust is just a way more modern environment. And I think in this audience, I don't have to promote Rust anything more than is really needed. One thing I'll mention, though, is the mono repos and the way that examples work in Rust were really defining features that make me adapt this whole environment. Especially the mono repo really helped with that decoupling ID. It made it really easy to just, make small examples, make small little iterations, and keep everything in sync. It did, however, complicate the open source sharing of some of these components, which I'm still looking into how to solve that. Because as you might expect, in a mono repo, everything starts to interconnect, and then it becomes harder to just share one component of it. Why did I choose Bevy? Well, this might be not a very flattering comparison because Bevy is way more than just a 3.js thing, but for me, it really was just a way to hit the ground running within the Rust ecosystem. But along the way, I discovered that Bevy actually has so much more to give, especially in, for me at least, the area of adding niceties to Rust, like how it deals with global variables in the form of resources. Stuff like that are just amazing. A second challenge was to spawn that irregular grid. You see it here in the background. So what makes Townscaper so interesting is that instead of taking a voxel grid approach, it's decides to curve this whole environment, which gives this signature organic feel to the whole environment. But you might expect that this is quite hard to represent with normal mesh data structures. And within these procedural modeling tools, you want to store these types of systems so you can start iterating on it. Like, oh, let's subdivide one of these pentagons further, or let's subdivide this triangle into 4 quads. If you can't store it, those sorts of procedures will start to be very complicated. So what's a data structure where you can store squares, pentagons, triangles? And I decided on a polyhedron data model. So it's like a mesh, but it can support up to n-gons. And with this data model, I was able to support operations like subdivision and removing an edge between 2 triangles, for example, to make a quad. The implementation is based on a half-edge data structure. For those who don't know, a half-edge is a way to very efficiently store these types of systems where you can have triangles intermixed with quads, intermixed with pentagons or n-gons. And I won't dive into very specifics, but you see that it's based on a pointer system where each half edge points to the next one and to the opposite, and in this way, there's always a way to transverse this data model, and you can start building functions that, for example, query one polygon out of this whole system, or or all the edges around the vertex. Here, I also show a bit of my approach to how I model these things, and that's keep it dumb, keep it simple, and move on. I've seen some half-edge data structures in Rust that use more involved pointer schematics, but just in practice, for me, it's turned out to always be for me at least, it was always nicer to just keep things very, very simple, very dumb. So these pointers are just use sizes at the end of the day that just point to a value in a vec. And this way I could get around the classic problem of not being able to represent a linked list in Rust. And yeah, I just also have just the advantage of just everything stays dumb. So it made it so that I could just iterate real quick at the cost of some nicer pointer arithmetic, which you could do if you actually fire some or add some like type legends to problems like this. All right, so with that data structure in place, we can do operations like this to actually spawn grids like this. I won't go over the specifics, but in here you see a procedure where it's basically a couple of subdivisions of a big hexagon, edge removals, and if you guys want to show, I can show you more specifics about this system maybe after the presentation, but let's not dive into specifics right now. The fun thing is that this also works on practically any surface, so a sphere is also not a problem. We start here with an icosahedron, and we start subdividing that a couple of times into lots of little triangles. We merge some of these triangles to quads. We start relaxing this whole system, and you're left with these lovely, groovy terrains. Then a third challenge, which is like, okay, we now have these great grids, but they're empty. Let's try to spawn some assets on it. And they're immediately met with the problem of like, okay, I have these nice assets and some tiles. I modeled some cute Dutch buildings also. But can we, like, how do we translate those things? The solution is actually quite easy. It's a trilinear interpolation. So what we do is we take all the input data. We essentially build a bounding box around all that input data piece by piece, where we try to find where of that mesh, a vertex in that mesh, where is it located in a normal space. Let's do that again. When we have a bounding box surrounding an object, take a vertex, then figure out the normal location of that vertex within this bounding box. And then with that normal location, we can actually interpolate it back into some other box located somewhere else. And if you then use a octoid, so let's say a cube but warped in some manner, where all the vertices don't necessarily nicely align but are warped a bit, then it actually becomes possible to take just a simply normally modeled mesh and translate it to this funky grid. The problem arises when you have components that span multiple of these sort of cubes, or where the bounding box is not all that easy to define. And in that sense, or in these situations, the solution was to actually use several small little bounding boxes of a initial asset, and then translating it for every one of these little bounding boxes into the corresponding associated cube in the world, if that makes sense. For that, we do need to specify all those bounding boxes, where those can be expected, and those were just stored in the code. I don't know how we're doing on time. I think we have a small little, probably some time left for some demo. Let me quickly share with you guys the link in the chat, so you can also play along if you want. It appears I cannot talk to the chat right now. Okay, we'll have to do that afterwards. Maybe that's better as well. Let me quickly run it just locally. Sadly, due to the edge detection not yet working, the edge detection is a feature that's currently hard to do with just WebGL. So you will not see these nice edges in the browser-based version. But this is the current project. So to reiterate on what we just, what I just showed you. First of all, now that I have you guys all here, I can tell you about some cheat codes in here. If you press the grave button, you can open up all the debug information, and you can start playing around with some of the parameters that actually generates this whole Earth. So these parameters right here actually control the the subdivision system that was just that I just showed. So you can see some of the effects of these parameters and how it affects the actual generation of the terrain itself. You can also see what happens if you now spawn one of these larger objects, spawning multiple of these tiles. Let me make a better example of. Here you can see what's happening a bit. So these are yeah, this is sort of the bounding box of this object. And you see that it tries to warp itself into place in all these cells. Yeah, and that's where we're at currently. So what's next in this whole project is to actually add wave function collapse for those in the know-how. That would make it possible to, right now you see that it's just a simple terrain model. This is marching cubes for those interested. But with wave function collapse in place, folks will not have to place individual assets everywhere. You could make way more interesting things where you can sort of paint something like city structure somewhere, and the algorithm will do the rest in actually giving that city structure shape, spawning assets. And the most amazing part of it is that based on what you draw, different structures could emerge, different assets, different tiles will start emerging based on specifically how you configure your city morphology or something like that. So yeah, looking forward to adding that. And yeah, the next steps of actually turning this into a fully-fledged game. So yeah, thank you guys for your attention. I'm Jos Veenstra. You can find more on geofront.nl. Yeah, it was a pleasure. Thanks.
Thank you so much, Jos. That looks so cute. And someone in the chat just figured out that it's unbelievable that there's no UTF-8 emoji for windmills. How dare they?
Yeah,
I also dug out the link from your slides and shared it in the chat so people can hopefully still chime in, check it out, and leave some questions for you here. Amazing project. I'm curious to see where it goes. I mean, you kind of hinted at the end now that it will go into what's the direction of a game, even though you said it's not clear yet. But it would be a shame if not.
Yeah, it's that was the original goal of seeing Townscaper, playing with Townscaper, and then being like, oh, this could be so great if it could be the basis of something bigger. You know, if it may even be. Yeah, I believe it could be as big as Minecraft at the end of the day. It's just a voxel world, but a bit more groovy, a bit more, cute to look at, as you said.
Yeah. Okay, we have a few questions. Let me ask you one before we switch over to a panel conversation with the rest of the folks.
Please do.
Did you open source your polyhedral or polyhedron implementation or any of your work that you?
I did. But I hinted at why I'm. So there is a crate called Hedron online, in which you can find some of that polyhedron code. I will say that it's terribly outdated due to the fact that I described in the presentation, where I decided to, just for project velocity's sake, adding everything to a monorepo. But it also meant that all my code became interlinked and very hard to share only a tiny bit of it. So I'm afraid that since I took Hedron out of that open source crate and into that monorepo, I no longer have shared those updates. And I'm not sure if I want to share the entire monorepo yet, because there's just a lot in there. And also,
would it be possible to share subparts via submodules or something like that?
Definitely, and I'm looking forward to doing that once things stabilize on this end. Okay.
Cool. Jos, amazing project, and definitely very ambitious, like you pointed out, to copy such an enormous project. Do you from all Oscar's knowledge sharing know how long he worked on Townscaper?
I think the whole trajectory, because he also built a great game called Bad North before Townscaper, where he explored some of the ideas, then perfected, I would say, in Townscaper. And I think that whole trajectory was around like 4 or 5 years, but don't quote me on that.
Yep.
So, yeah.
Yeah,
we'll see how long this takes.
Some work ahead of you.
Yes, definitely. But looking forward to it.
Okay, Jos, hope you get a big hand from chat, and I'm gonna pull the rest of the panelists on, and then we can go across the entire remaining questions. There's a bunch of stuff that we still can talk about here today. Okay.
Perfect.
Let me get François and Lorenz. Welcome back, guys.
Hello.
Hey again.
So I have hidden all the questions that we had to skip over before. So I'm encouraging everyone in the stream to jump over to the Q&A site and vote on the questions that you care the most about, so that you can make sure to get through them in order. And they are marked by who they address. So that should be easy to identify. And yeah, the first one is for you, Lorenz. Why do we have these two separate worlds that you kept talking about?
Yeah, that is actually quite a genius move, because having two separate worlds means we can extract the state of the last world, preparing and rendering it in parallel by computing the current tick of our game world. So it's very nice for parallelization.
Okay, so that means I'm picking up the next question that is totally related to this. That means there's a whole lot of duplication going on then, is that correct?
Yeah.
And how heavy does that impact? Is that copy on write, or is it just cloning everything?
It's mostly cloning everything, but most of the stuff only gets cloned once unless you change it. So like usually when you load your mesh, it's loaded once. Do you need to load more than once? Probably not. So it's just happening in one loading state, and then it's there for you to use.
But what if you update the mesh every cycle?
Yeah, then it's going to get updated each frame, and there's no way around that. Yeah.
Yeah, to add on that, entities and components are cloned, but assets are extracted, and they aren't extracted every frame. They're extracted
only
on
if they change. Yeah.
Cool.
Okay, so the real heavy stuff is not going to be cloned. That's just referenced then from both worlds. Okay.
Exactly. Yeah.
Unless you
Well, that
usually
makes sense.
model things around. Like I'm pretty sure that I'm committing like all sorts of sins, rendering sins in this whole system. Just scraping, cutting corners and stuff.
The more you know, the more paranoid you become about.
Yeah, right. Yeah, yeah.
Yeah. I mean, isn't that a general learning? Ignorance is a bliss, right? I mean, you will see it otherwise in your FPS anyway.
Yeah.
François, would it be cheaper to build a server farm in Cart's basement? Oh yeah, that's a great question.
Yes, but then it would cost electricity for cards. He would have to pay more for more bandwidth, and he would have a lot more time to do administration instead of developing for Bevy. So, do we want a Bevy card admin or card developer?
Would you like to have that basement?
I don't have a basement, so no.
Yeah,
that's a problem.
Yeah.
It's also generating a lot of heat, I hear, having a bunch of hardware running there. So I'm not sure if that's a
We're
good
actually talking
idea.
about having a first server at Cart's home to get us started.
Oh, nice.
Oh,
okay.
You guys are considering
this
building local. Ah, okay, cool.
So this question wasn't as ridiculous after all. Okay, François, next one is also for you. You mentioned Flip. I guess this was this NVIDIA tool. Can you describe what it does? Why is it better? Why is it different?
Describing what it does, I can't. There is a paper that I read and didn't understand yet. But the idea is to have image comparison closer to how humans compare image instead of a pixel value by a pixel value. So the idea is to have a difference that would be like what humans notice as a difference.
Is that some machine learning bullshit then, or how does that work?
Not a machine learning bullshit, but it's something used for machine learning.
Okay.
So we're tokenization.
It's used as classification for image generation algorithm to be able to say how close we are to the target image. But yeah, so it would be easier, for example, for the example I showed that changed every run with a few pixels on the edge or stuff like that. It's not noticeable by humans, so those algorithms wouldn't pick these differences.
And
Interesting.
this tool is free to use. Whatever we can integrate it in
there
our
is a paper
pipeline.
that describes how to do it, so you can recode it. But yeah, there is a default implementation.
Well, if there's a
that
paper,
you can
doesn't
use.
mean that it might not be copyrighted, right?
Yeah.
As we recently learned. Yeah. Another one for you. How does the software renderer work? How much of the rendering pipeline is tested this way? Does it implement the Vulkan API, Web GPU, or does it start earlier in the render pipeline?
The software renderer, it will depend on the platform. On Linux, it will be Vulkan. On Windows, it will be DirectX 12. On macOS, it will be Metal. And then for each time, it's not implementing WGPU. In WGPU is implemented on top of that. So it will still use a software renderer. And after that, how it's implemented exactly, I don't know. I'm really not into hardware and drivers like that.
So it's something that we get actually for free from the different APIs. There's sort of like a different device that we can select explicitly on machines that, like you said, for example, in Vulkan, there will be some software rendering device that we can pick.
For Vulkan, there is a LLVM pipe that goal is to have a software renderer. And on macOS and Windows, they ship one built-in.
Okay. And did that ever turn out to be different from the real results?
On Windows, yes.
Aside from Windows?
No.
Okay. Cool. Lorenz, a lot of things seem very standard, like checking visibility. Are there reusable building blocks one can use from the Bevy render pipeline, or do you have to copy-paste?
You just copy-paste the data you actually need for your pipeline. So stuff like checking the visibility already happens in your app world. You don't have to, you are actually extracting the visibility component from the app world to check if the entity is visible. So
okay,
you only extract.
We saw there is some code in your custom render pipeline that actually checks that if it's visible, right?
Exactly.
I guess this is just a simple example of something super standard that you still had to do in your custom path.
Yeah, I have to check. I'm querying each of my custom sprites, and I don't know in that position or in that specific part of the code if the sprite is actually visible on the screen. And the visibility component from Bevy itself is run right before the extract stage is run. So it checks for each camera, is the object actually visible? But I still have to check it before I extract it if that's the case. That's not.
So you could still render it if you wanted to,
yes,
and I don't know, move the
could.
vertices into view or something.
I mean, yeah, we are talking in the ECS context. We cannot, just because the component is not visible, we cannot remove it from the world. So it's still there, and we have to check it manually before we extract it. But the checking part is done for us. We are just doing a Boolean check there.
What I'm reminded of something Alice wrote down somewhere, where she was actually talking about if they could actually hide objects on, not visibility wise, but just actually hide disable objects on a ECS level.
Yeah, there is a few PRs and RFC at the moment for disabling completely entities. But there are a few side effects that we have to think about before letting that.
Right. Yeah, I can imagine. Yeah. Interesting. That might help.
Yes.
Yeah.
Now that you're talking anyway, did you open source? Oh wait, we talked about that one already. Hey, the good news is the next one is about you as well. Does the subdivided mesh shape vertically repeat on the sphere? Holy crap!
Does the subdivided mesh vertically? Yeah, I get what you mean. Sadly, no. It's just an extrusion, but it could. You would have to create a different data structure. A half mesh wouldn't cut it. You would make it, because on a half edge mesh is essentially a surface definition. But if you can take that up one dimension and make that a solid definition of a solid, of a three-dimensional thing, then you could actually do that. And you would, and it's actually, you probably want to do that for like a sphere, because what you now have as a problem is when you extrude too far in that spherical example, the things that you spawn on those extruded parts start to become flatter and flatter and flatter, just to the nature of how those cells expand. So a house spawned in the inner circle would be very tall, and a house spawned on the edge would be like very small. So I was actually looking into this. It's not as crazy as it sounds. So thanks for the question.
Yeah, definitely. Sounds like this was a thought you had anyway. Cool. Jos, I heard there were efforts to remove. I think this is brand new for the ongoing conversation. I heard there's more efforts to remove the need for a render world. Would it be possible to remove the need to clone everything into the render world? I guess this is more for all of you. If you heard anything about this.
So yeah, there are talks because the ECS is not the best data structure to talk to the GPU, but we don't know yet what we will have next. And now we still have to clone everything because the idea is to allow the main world to run and modify while the render world is also running. So we can't have both access to the data, so we have to clone it.
Right.
I mean, this is a lot of half knowledge on my end now, but isn't a modern API like Vulkan these days, compared to the old days with OpenGL, more or less like non-blocking anyway? Like, how much do we actually gain from separating the whole process up to a draw call into basically a separately threaded, duplicated world? Like, do we know how much this actually runs in parallel?
I know it does run in parallel, but yeah, we had big gains when we implemented that, but I don't know if it's still true with modern APIs. But also we gained the ability to have different frame rate. Well, not frame rate, but run the different world at different speed. So rendering world would run at the frame rate, while simulation world would run at the rate you need.
Okay, so it is something we also use to skip frames, essentially, if we can't deliver the frame rate that we want.
Yeah.
Okay, gotcha.
Or to run the world faster and just extend one frame every 5 run or something like that.
Yeah, that makes sense. Do we measure code coverage since we aim to increase unit test usage?
No.
Is that something that's planned?
I don't think it's a good idea because it gives us a metric, and once we have a metric, we want to move toward that metric. And again, I don't think aiming for big code coverage is a good thing. We want to increase it, but yeah, it should be focused on specific part like the CS or reflection, but not everywhere.
Yeah, I love that comment in your slides, where it's like, okay, even though it sounds nice to go for that 100%, it's maybe diluting our efforts into actually doing something meaningful. Yeah, very nice.
Lorenz, when you write the vertex buffers, is that a blocking operation? So does that block the world while extracting?
So we are writing the vertex buffer in the preparation stage, and we do so by basically calling a write buffer command and passing it into our render queue. And to be honest, I do not know what the rendering queue then does exactly with the buffer and if it runs in parallel. My guess is it really depends on the device, and you actually bus between the GPU and the CPU part. And that probably is not in parallel because it's probably just one bus. But this is just my guess.
So it's probably also dependent on which API is actually running under the hood then, depending on the platform.
I guess more so on the hardware. But don't quote me on that. I'm not sure. This is more outside of the part of Bevy and more into WGPU.
Another one for you. Do you have to create _bind group layout, like this whole function call, every frame? I guess that was something that looked rather generic.
Yes, you have, in case it changes, of course. Some pipelines don't change, so they don't have to do that. Others, if you want to have some change that you want to communicate to the GPU, you have.
So you could put like custom logic in there that makes sure that it doesn't call that unnecessarily.
The best example in my example was the quad mesh. It is just queued once and communicated once to the GPU, and then the RAM is there. And all we do is say to the GPU, hey, you have it here, load it please for my shader. But we don't have to copy it again.
Yeah. Jos, aren't your pointers just ECS-like entities? Was using the Bevy ECS no option? I think this is
Could
talking
be.
about your custom
I indeed
structure.
have a very, very good point. I have seen half mesh implementations using ECS. I decided against it because I wanted to separate again that idea of separation, where you see this in Rapier as well, where it's for example, especially for these procedural modeling libraries, it's nice to be able to separate that from, for example, Bevy. The whole procedural pipeline does not need to use Bevy, which makes it, for example, really lightweight if you just want to run it on some server, or if you would want to use this for some other application, like I've been dabbling with the idea of making it a visual programming language, one of those graph-based modeling things.
Another tiny project.
Yeah, another tiny project. Yeah, why not? No, but for those types of situations, it's just nice to have like a date, like the whole thing being one struct. That's one thing, and not have that tied to also an ECS, in my opinion. But if you want to tie this to an ECS, like go for it.
I think the question was more like, isn't what you're doing there sort of remodeling what an ECS does? Because you're using U-size indices into probably some contiguous array of data, right? And and instead, basically going around this whole ownership problem that you would have, as you pointed out, with linked lists in Rust.
Yeah, but like, why not do that also for meshes? Like, we also use meshes with vertices, or like meshes with triangles, and those triangles are just U-size or U32 pointers to vertices. We could technically also do something like it. I find it just a sort of a convention in the 3D data modeling world to do it that way. So I modeled it after those types of systems. But you could totally do that. It's indeed modeling the same problem that an ECS is trying to solve. So you could do that, yeah. What do you guys think? Or, it is a panel discussion, right? Like,
yeah, of course, everyone could speak up, please.
Yeah, it could be super naive what I'm doing. Like, I've got no clue.
No other ideas, I guess.
No.
Cannot say anything to that. Sorry.
No worries.
Lorenz, couldn't the vertex buffer layout be automatically deferred based on the type we put into the vertex buffer? I mean, this is sort of a Rust struct, right?
Wait a second, I have to check that. Yeah, we probably can. No,
it's actually a second question that's basically the same, just for the syncing of the data between the shader language.
Yes, I mean, Bevy provides us some macros to make it easier, like the asBindCrop macro that lets us easily generate the layout from that and also the data. But for the vertex buffer layout, I think there is none of this kind, and we have to specify the inputs by hand. But I could be mistaken.
But do you think it should be possible? Like, after all, they are basically in sync, right?
Could be possible, of course. I don't see the problem of creating a new proc macro that does exactly that. That creates some sort of buffer layout for the vertex input buffer, depending if it's an instance buffer or a vertex buffer. Should be possible.
Yeah. And the similar question goes here. The vertex input in the WGSL language is also basically a copy of what we have in Rust code.
It's a copy, yeah. You have to define it on the Rust side, and then you have to define it on the WGSL side. And no, sadly, there is no good tooling for that. I mean, we don't even have a fully functional language server for WGSL. I feel like graphics programming in general is always left a little bit behind. At least
with Bevy, we could imagine generating the WGSL code from the Rust side and importing it.
Yeah, that's what I
completely skip that step and go to Rust GPU and write our shader directly in Rust.
There is hope. Rust GPU looks very promising. And having something like that would be a blessing.
Wait, that means that allows to write an actual shader in just normal Rust code, or is that some sort of subset of Rust?
Exactly. That would be so nice.
Oh, wow. Okay.
Just testing. The worst case about writing shader programs is testing is really, really hard. You either get it right or you get nothing back.
It's a subset of Rust in the meaning that I think it's no STD, but yeah, otherwise it's Rust.
Wow.
Okay. That would be cool.
Yeah, also for compute shaders, that would be really nice.
Yeah.
Exactly. Wow.
And you can run the same code either on GPU or CPU, depending on your workload or stuff like that.
Oh,
that sounds awesome. Maybe that would finally lead to the whole machine learning stuff to be done in Rust and not in Python.
Yeah.
But the types, did that ever happen to you while working on these projects, that these types were running out of sync? Like, is that actually even a problem? Lorenz?
Yeah. I cannot remember a specific part, but defining some variable wrong and Naga, the underlying, I don't exactly know what Naga is, the WGSL live linter, something like that, doesn't tell you anything about it, and it just does not work. And then you are struggling for hours to find that tiny little mistake. So yes, I'm looking very much forward to having a full implementation on the Rust side that I can probably lint, where I can see my mistakes before pushing it to the GPU. As I said,
when you have,
there's just tooling for anything GPU related. It's just very bad in general.
So, but do you get error, like proper error reporting when you send it to the GPU? Is that at least the point where you get some proper, like where the problem is?
Something. Yeah, you get something. I mean, when you bind the wrong kind of variable, for example, you bind a vec2 instead of a vec3, then you get something back from Naga, and it says something like that. Oh, type 25 doesn't confirm with type 24, but it doesn't tell you directly what is happening. It just tells you the line and two type IDs don't match. So, maybe there are better toolings that I'm not aware of. But the way I do it, or the standard way, is sometimes you have to take your head and smash it against until stuff works, and that could take hours. Yeah.
Yeah.
Okay.
Been there, done that.
Yeah. So we are done with the questions. Is there any other thought that you guys have that you wanted to mention now throughout the conversation?
Well, for me, I'm just looking forward to rewatching Lorenz's presentation and basically sort of having that and this whole project next to each other and being like, oh yeah, okay. Because I was doing some custom shader stuff, but it's very copy-pasty, very surface level analysis of what was going on. So it's super nice to now have a blueprint of, all the layers.
Do you have to already go custom pipeline as soon as you need a custom shader?
No.
No, totally not. But if you want some custom input for some custom shader, you're starting to look into the pipelines.
You should be able to do that with the material abstraction.
That's no, that's for sure. I was trying to look for ways to get around the fact that the depth buffer doesn't really work on if you go for WebGL.
Just go to WebGPU. It's easier.
Yeah. But sadly, I can't tell people to switch to WebGPU yet to run this demo. But I would love to, though. Oh, love to.
Well, I think you can probably, right? You would probably have to link to a very sophisticated instruction how to enable it, though, on some browsers.
Yeah, but that's sort of.
There's hope, right? Didn't Chrome just release WebGPU? I saw something like 70% coverage already, right?
Chrome released the WebGPU almost 1 year ago, only on macOS and Windows.
Oh wow, really?
Yeah.
Yeah.
Firefox released in the nightly only on Linux and Windows. And Safari Technological Preview starts to have a working WebGPU implementation.
Oh yeah, I saw your message one day, like a few weeks ago, right? That we have our examples now working on Safari.
On today's version, everything works except for Bloom.
Oh, nice. That's promising.
Yeah,
And for our projects, it will basically be like free, right? We don't have to adapt the projects there unless you go custom and do shit that might not work on
We have
WebGPU.
something that we don't know yet how to do. It's to have the same binary, wasm binary works for WebGL2 and WebGPU.
Oh, yeah.
It
So
should be
you basically
possible,
have
but
to-
we don't know yet how to do it.
Yeah. So right now we have to bundle both if you want to support both. Yeah.
Run WebGPU, and if it crashes, go to WebGL2.
Damn.
Well, at least then you don't download both at the same time right away.
Yeah.
That's already an advantage because those things are still quite huge, right? Okay.
Cool.
Guys, I would want to wrap it up by one round of each one of you telling me what's the biggest thing you are excited about in the upcoming or in a upcoming Bevy version. Like anything you know that is going to happen or that you would want to happen. Like it doesn't have to necessarily be in the next release. But what do you miss? Jos, you want to start?
Sure. What am I missing right now? Yeah, I guess. So Lorenz hinted at some important component. I know this is not related to Bevy probably, but if it would just be a lot less painful to start toying around with shaders, and also just debug once you start doing something wrong, that would help out so much with just creating so much, making creating shaders just so much more joyful. That's sort of a hiccup points that I would love to see solved. So I would say that. But yeah, that's not really due to Bevy. It's more like tooling around it.
Yeah. François, what about you?
Well, the next version of Bevy will have a lot of rendering improvement that you don't have to write shaders to use. So that will be nice.
Oh,
and
nice.
Of course, relations.
Is that going to be in 0.14?
No.
Oh.
But it's coming.
Yeah. Nice. Okay. What do you guys look forward to relations? Is that something you're excited about, Jos, Lorenz?
First time I'm hearing it actually. What it's about?
It's a way to link entities without having to hold an entity in a component. It should auto-update and a lot of nice feature. But I think it's hard to see all the improvements it will bring to us.
Cool. That sounds very exciting. I can
Yeah.
already imagine a use case for that.
Yeah, I've seen some implementations of that during my day job, so I'm also looking forward to seeing those two toy around with each other. Because but I don't know how much I can share about that, so I'll shut up. But no, it's great that the rendering. What type of rendering improvements, François?
Well, you should check out PC Walton's Twitter. It's like basically a one-man rendering machine.
All right, I will.
And
also, maybe you have specific examples.
Yeah, I will. Thanks.
Yeah.
Awesome.
Lorenz, how about you?
I have so many things I'm looking forward to. And the first one, I mean, I'm probably sharing this with a lot of members of the community. That's Bevy UI. I really want to have better tooling for UI. It's just something like.
Is it something that we need Bevy to change for, though?
No.
Like, for example, Bevy, like a UI editor?
Bevy UI is it does everything it should be. It's just we need better tooling and better ways to interact with it. If you don't use any outside tooling and you just try to do something with Bevy UI, it's painful. Describing a simple UI is hundreds of lines of code, and then you want to make tiny changes, move pixels. You have to reload, recompile. Just have some great toolings and hot reloading that you don't have to program yourself. That is unified and everybody agrees on. That would be great.
Yeah, I can only agree with that one. I mean, having a what you see is what you get editor for the Bevy UI would be amazing. I'm losing a lot of time on that stuff.
Yeah, same. I forgot about that whole pain. But yeah, that's also where this project is now a bit stranded on getting some good UX in there. or in UI, UX. Yeah, some more involved tooling around that would be fantastic.
I just thought about some news that I saw today. There was a new release of this Firefox engine. That's another big Rust engine, right? And I don't know if you've come across the release notes, but what they released now is a version that actually does support hot reloaded like game logic. So you don't have to recompile engine and all, but basically you can sort of script in Rust your game as if it's a scripting language, if you will. So I was wondering, probably specifically for something for you, François, is that something that we could pull off on Bevy as well?
In theory, yes. In practice, we will have to try. And yeah, there are a lot of ways that it can go wrong. So yeah, hot reloading is possible, but you have to use the exact same compiler.
Well, I guess that's probably no problem if we are
it
talking about iterating on your
machine.
local machine. Yeah. And I think that's the biggest use case of this, right?
Yeah.
But
yes, so we have to limit it to that precise scenario, and it should be able to work.
That would be amazing. Yeah. Cool. Okay. I think that's about it then. Any last thoughts?
No, just thank you so much for organizing this, Stefan. It's
Thank you for asking.
Yeah, it's a pleasure. It's amazing.
You're looking forward to the next.
Definitely.
Of course. That's a great segue for me to ask everyone on the stream to please reach out if you have anything you want to share in this sort of setup, or if you know someone that you would like them to share what they're working on because it's interesting stuff. Then please reach out to me. I'm always looking for content for this. And yeah, guys, it was amazing. Super interesting presentations, a lot of different stuff. And I'm happy that we can basically call this one a reference for building a custom rendering pipeline from now on, at least until radical changes are implemented in the next release, probably. Okay, guys, I'm going to stop this one here. Thank you so much in stream. Give a big shout out to all the speakers, and see you next time.
See you next time.
See you.
Thanks for having
Bye.
us.